When I left, the question concerned what my father had asked me so many years ago in my first year of studying physics. And the question was this: suppose you have a flower pot, and here's a flower pot, and the flower pot and its flower and the whole works, we know what it weighs. We'll pretend it weighs 1 pound. And down here we have the client. This is my father's client. And let's pretend it's 1 foot down here, 1 foot to the head of the client. And the flower pot falls on the client's head. The 1 pound flower pot falls down 1 foot and strikes the client in the head. And here it is. There's the flower pot down on the client's head, falling down. I guess the client's going to have an expression like that after he gets hit. And the question my father asked me was, how many pounds of force does the 1 pound flower pot exert on the client's head after it's fallen a distance of 1 foot? And I asked you that question. Remember, there were several possibilities, several ways you might answer me. One, you might say, well, the answer is it will hit with 7 pounds of force, or it will hit with 8 pounds, or 10 pounds, or some certain number of pounds of force. And the other answer that you might give me is that you might say, well, I can't calculate it, but I know that anyone who had studied physics seriously for a year should be able to answer that, because you know the weight of the flower pot, or the mass of the flower pot, to use fancy words, and you know how far it's fallen. And by knowing how far it's fallen, you should be able to calculate its speed. And once you know its mass and its speed, well, then you can calculate how much force it hits with. And it's not hard. That's the second possible answer. The third possible answer that you might say, well, you might not be able to do it with just 1 semester of physics or a year of physics, but certainly a professor, an Einstein of physics, could calculate this and could then come up with an answer. That's the third possibility, I guess. And the fourth possibility is that it is unanswerable by anyone. By anyone. It's unanswerable. Even Einstein couldn't answer it. And I told my father, after thinking about it for a while, that the problem was unanswerable. No one could answer it, not even Einstein. And my father said to me, what are you talking about? You've been in the university for a semester? Look, if you can't work it out, then just get a scale, get a postal scale, get a scale like this, the numbers in front. 1, 2, 3, 4, 5, and drop the flower pot down on a postal scale, and that way you can read how much force it is. And I said, yes, Daddy, but you really wouldn't want to do it that way, because you'd break up the scale. After all, if you dropped a 1 pound flower pot on a nice postal scale, you would break it up. What you'd have to do is you'd have to put some kind of a blanket up here. And if you think about it, Daddy, if you put a little blanket there, you wouldn't get quite as much force. And of course, you still might break the scale, so you put more blanket on top and more blanket. And the more you protect the scale from being broken up, the less the force is going to be. And so the force depends not only on how much the flower pot weighs and how far it's fallen, but it also depends on how much blanket you put on top of the scale to protect it from being broken up. Now, I want to see, my father had in his mind inadvertently made a mistake that many people make. They talk about something, many people talk about something called the force of a moving body. And they assume that when you have an object that has a certain weight and it's going at a certain speed, that to stop that object, a certain force is required. Or if that object runs into something, it will exert a certain force, the force of a moving object. But it turns out that's entirely wrong. A given object, say an object that weighs 1 pound, moving at a certain speed, say 5 miles an hour, A given mass moving at a certain speed has no force to stop it. There is no such thing as the force of a moving object. Now, later on, not today or tonight, but later on, I'm going to tell you that if you know the mass of an object and you know how fast it's moving, there are things you can tell about it. There's something called its energy I'll talk about later on, its kinetic energy, and there's something called its momentum that I'll talk about later on. But there is no such thing as the force of a moving object. You see, a moving object can be stopped by a big force or by a little force. If you have a little force trying to stop a moving object, the little force will take a long time to stop it. But it'll bring it to a stop gradually. By dragging your feet on the ground, you could eventually stop a railroad train. It might take a long time and wear out your feet, but you could. On the other hand, you can stop an object with a large force too, but when you use a large force, then it stops very quickly. And so you have to know how you're going to stop the object before you can talk about the force. And the thing that my father didn't realize, and perhaps that I suspect that you might not have realized, though you can be proud of yourself if you did realize it, but the thing that most people don't realize is that the thing that's missing from this problem is some supposition about how much distance the flower pot has to come to a stop. You see, when the flower pot hits the client's head, it doesn't come to an immediate stop. There is some give in the skull, and there's some give in the neck, and there's some give in the spine, and there might even be some give in the knees, and there's some give in the heels of the shoes. And coming back up, maybe the person has some hair, a wig hat, or a hat. And even there is some give in the flower pot itself, and there's some give in the floor below, particularly if it's a wooden floor. So there's a little sponginess, and it's that sponginess that has to be taken into account. That is critically important in analyzing this situation. So let's try to analyze. Let's try to analyze this thing, and let's say that the thing has, let's just pretend it fell 1 foot. Let's pretend that if we add up all the give in the flower pot, in the hat, in the wig, in the skull, in the neck, the backbone, the knees, the heels and ankles, and the floor, let's just pretend that there's 1 inch of give. Later on, we'll change that assumption, but let's just begin to pretend there's 1 inch of give and the flower pot falls 1 foot. Then, given that extra piece of information that there's 1 inch of give, now can the problem be answered? And the answer is yes. And you say, but how? We still haven't dealt with anything falling body speeds. I know that can be done, but we haven't talked about it yet. Well, we have talked about it. You see what we have here? What we have here is another lever problem. Now, most of the lever problems that we've talked about so far, and of course they weren't all levers, but some of them were like a syringe or a block and a tackle, and that's not really a lever, but it works all on the same principle. What we still have here is something that works on the principle of a lever. Even if it's not a lever, it's working on the same principle. And that's the principle of work, that the work that goes in is equal to the work that comes out. The force that comes in times the distance that comes in equals the force that goes out, multiplied by the distance that goes out. You say, still, but what are you talking about? Where are the 2 arms of this lever? Well, this is a lever that does not extend through space. This is a lever that extends through time, and the 2 arms of the lever are at different places in time rather than different places in space. Look what I'm talking about. First of all, the flower pot falls 1 foot, or 12 inches, and it weighs 1 pound. So how much work goes in on the way down? On the way down, how much work goes in as it comes down here? Well, 1 foot-pound. What is 1 foot-pound? 1 foot-pound is 12 pound inches. All right, 12 pound inches is 1 foot-pound. And what comes out? All the work that goes in must come out. When it comes out, how much does it move? as the energy goes into the pot coming from gravity, it's falling down. After it hits the head, it begins to slow down, and the energy comes back out of the pot and, of course, goes into the client's head. And while the energy is coming out, how far does the pot move? Well, we already agreed that there is 1 inch of give, and so here is 1 inch. 1 inch of give smashing into the head. What force pushing 1 inch does 12 foot-pounds of work? 12 pounds pushing 1 inch does 12 inch-pounds of work. And so the force down here has to be still 12 pound inches, but since it's only 1 inch, it is 12 pounds times 1 inch. That's what this thing is equal to, 12 pounds. And up here we had 1 pound times 12 inches. There you go, and that equal that. Same work. Work in equals the work out, but here it's 1 pound times 12 inches falling down, and after it hits the head, it's 12 pounds times just 1 inch. Of course, you can see what the answer would be. Now, let me ask you another question. You say, well, I don't think there's that much give, really. I don't think there's that much give. I think there's only ½ an inch of give. Now, can you answer what the force would be if there's only ½ an inch of give? Well, you could go through the whole calculation, but on principle, just by thinking about the principles, can you see what the answer would be? If there was only half as much give, ½ an inch instead of 1 inch, but the same amount of energy comes out, then the force must be twice as great. Isn't that right? So you'd have, instead of 12 pounds, it would be 24 pounds for ½ an inch, for ½ an inch of give. And now it's conceivable, very conceivable, that if it was a bald-headed person like me standing on a concrete floor, stiff back, fused spine, maybe there would only be 1/4 of an inch of give, which is half of a half. Let's pretend there was only 1/4 of an inch of give. Then what would happen? Well, if it was only ½ an inch, it would be 24 pounds. So again, if we make it half as much motion, to get all that energy out, we're going to have double the force. So then it would be what? 48 pounds. If it was only 1/4 inch of give, then it would be 48 pounds of force. Now, I want to leap ahead. Let's pretend that you have a situation where there is absolutely no give at all. I mean, I'm a marble statue, and it's a marble flower pot. No give at all. By the way, it's not true that marble has no give, but we'll just pretend. Let's pretend it has no give, and the thing drops down on the head. What are you going to do then? Well, then there's 0 give. How can you reason about what's going to happen when the give is 0? Well, of course, you could stick 0 into the equation, but when you do arithmetic with 0, you get in trouble. If you add and subtract 0, it's pretty easy. Even if you multiply with 0, it's easy. But when you begin using equations where you have to divide with 0, you can get into big trouble. So we'll do the favorite trick of a real physicist. Instead of asking the question that I just asked, what happens if it's 0 give, we'll ask some other question. We'll say, what is 0? How do you get to 0? Well, maybe you start at 1, and then you go to 1/2, 1/4, 1/8, 1/16, 1/32, 64th. You keep on dividing by 2. And how many times do you have to divide by 2? Well, if you divide by 2 forever, you'll finally get pretty close to 0. So let's think of what happens. Instead of 0 give, let's imagine that the thing gets to be less and less and less, and look at the trend. And we can see what the trend is. When there was 1 inch of give, there was 12 pounds of force. When there was ½ an inch of give, there's 24 pounds of force. 1/4 of an inch of give, 48 pounds of force. You can see that each time you make it only half as flexible, you cut the give in half, you double the force. Now, how many times do you have to divide by 2 to get to 0? Well, you have to divide by 2 forever and ever and ever, and you'll never get to 0, but you get pretty close. But each time you divide by 2, as far as the give goes, you have to multiply the force by 2. So the force doubles and doubles and doubles and doubles and doubles. And if you keep on doubling a thing long enough, you'll get to a bigger and bigger number. The number becomes huge. It approaches infinity. So that if you ever made a thing that had no give at all, and you dropped something on top of it, the force would be infinite. And by the way, it doesn't matter what the weight of the thing is. Of course, it doesn't have to be a flower pot. Since the force is infinite, it could be half a flower pot or a quarter of a flower pot. It could even be a pea. You could take a thing as small and as light as a pea, and if it dropped onto a flat surface, only maybe 1 inch down, a pea just dropping 1 inch down, but that pea had no give at all, and it dropped just 1 inch onto a surface that had no give at all, then in theory, the force would be infinite. Of course, what always happens is in any real situation, even if it's made of glass or diamond, there is a little give, and that's why the force is not infinite. But we're very close to an important problem in physics. Long ago, what I mean by long ago, maybe in the time of Galileo and certainly by the time of Newton, people began to wonder about what matter was made of. And there was always an idea that matter was somehow made of something called atoms. Of course, nobody knew what atoms looked like. I'm talking about way back in the olden days, in the days of Galileo and Newton, if those are the olden days. Now maybe people think they know what atoms look like. Maybe they don't, but we'll come to that much later if we do at all. But back in the good old days, people had an idea that an atom was a small thing, probably a small little ball of some kind, and that it was absolutely unchangeable. In other words, it didn't do anything. It was one little ball. It didn't change its shape or change in any way. And why did it not change in any way? Because an atom is supposed to be the smallest thing there is. Now, if it is going to somehow change, it must be made of parts. For example, if it's going to change its shape, it must be made of two parts, and the two parts must move further apart or move closer together or move around each other. You see, for a thing to change its shape means that it has to be made of parts, and these parts have to somehow rearrange, and that's how things change their shape. So if an atom was to be perfectly unchangeable, then it could not change its shape, which would mean that it would have to be a rigid sphere with absolutely zero give. And they reasoned that if two atoms ever hit each other, and heavens knows atoms hit each other every day all the time. Whenever I put my hand down, atoms are hitting the table. But whenever atoms hit each other, if the atoms were these rigid little hard balls, then the force between the individual atoms would have to be infinitely great if the atoms could not change in any way. And that bothered people so much way back in the days of Galileo and Newton. Not all people, but it bothered some people so much that they reasoned from that atoms could not exist. Because if they did exist and they were unchangeable things, then every time two atoms hit each other, the force would have to be infinite. We might come back to that again. Of course, maybe you could avoid that by saying the atoms never really do hit each other. They just get near each other. Of course, when they get near each other, then somehow they have to stop moving. They have to get the idea before they hit, for if they hit, holy cow. So there was another group of people that said there were atoms, okay, but they never touched each other, and they never could touch each other because the force would be infinite if they ever did come in contact with each other. Well, it's funny, you don't have to, you can take a simple idea like the flower pot falling on the client, and you can, from that, get some fairly deep ideas, like the ideas that bothered some of the first physicists to think about atoms. You know, when you think about physics, it's like walking in a cave. I was one time a kid with my parents in the Oregon caves, and it was a very impressive and memorable experience being a little kid in the Oregon caves. And as we walked through the cave, you'd see these little trails going off to the side, and the guide had several times told us not to go on them. Of course, it was quite dark down there, so I didn't have much thought of going on them. But he said some of those trails led to unexplored parts of the cave, and it always amazed me how close we were as we walked through the known part of the cave, just a few steps to the right or left, and we'd be on the trail to a deep, unexplored part of the world. And that's how it is with physics. These ideas, you can take 2 steps off the main trail in physics, and you will be in a very strange and mysterious world. And in fact, the teachers who first teach physics in your first classes in physics, in fact, for quite a few years, the purpose of the teacher is to keep your feet on the known trail and not let you go off on these tangents into thinking about things like the collision of atoms and what happens. Because if you go on that trail, you will get over your head and into a very dangerous part of the cave very, very quickly before you have experience to handle it, if anybody has experience to handle it. Of course, those things are now understood, but I'm talking about how people saw them back in 1600, time like that. Well, let me come back now that you understand the thing. Of course, it would be nice for the what the client needs, of course, is a hard hat, and I want to talk to you about a hard hat. What's important in a hard hat? Is it the hard hat? Supposing if you've ever seen a hard hat, you know there's a hard hat, and inside the hard hat is a construction worker's hard hat. There's a shell, and then inside there is some webbing, and it's the webbing that actually sits on the person's head. Now, supposing you took the webbing out and you just had the hard hat by itself without the webbing, you just took the hard hat like so, and you just put it on the person's head. Now a person would have a hard hat. Would it do any good? And of course, the answer is, well, it'd be better than being hit by a brick, but it sure would be pretty bad. It's very important to have that webbing. And you can see what that webbing does inside what the purpose of that webbing is in there. What the purpose of that webbing is, or foam, is to make the thing to have some give, more give. And it's that give, that extra give, that protects the person from being hit in the head when something falls. Now in this world, we call the things hard hats. But it's very conceivable, since the important part of the thing is really the softness, that on some other planet in some other galaxy, the things are referred to not as hard hats, but as soft hats, which might be even more appropriate than calling them hard hats. Well, so finally we finished with our talk about levers, starting out with levers and pulleys and wedges and knives, block and tackle and hydraulic syringes, and finally this last thing, which was not even a lever in space. At least all the others up to now were levers in space, but finally we ended with a lever whose arms extended through time. And you might say, gee, these are all very interesting things. Each one of these is like a little toy, and we can stop and play with it in our head for a while, and then we stop and play with it in our head. And each one of these things is truly interesting in its own right. But at this point, I want to tell you what supremely delights physicists, and why I've told you about this thing. I've told you this whole story up to now to show you something about what delights physicists. What delights physicists is not so much really the individual levers and pulleys and gears that I showed you. What really delights physicists is that all of these things have one explanation. There is not a different explanation for the gear, and another explanation for the inclined plane, and another explanation for the screw, and another explanation for the falling flower pot. There is just one unified explanation for all of these things, even though they look so different. There's just one explanation for all these different things, and that is that the force that goes into the thing multiplied by the distance, how far it pushes, is equal to the force that comes out multiplied by how far it pushes when it comes out. Now, if it pushes a different distance as it comes out than when it goes in, then the force on the way out can be different. And it is that principle, the principle of work, that supremely delights physicists. So much for that idea, but it's an important one. We started out our talk on physics for the real world by going back to the beginning and asking about physics and chemistry and astronomy. and looking at the problems that got them started. Each of these sciences was started by a particular problem that many people worked on over the years. Each group of people making a little progress, but never solving the problem completely. And the problem was always a tantalizing problem, which kept attracting the smart people to wonder about it. And we just finished talking about the problem that started physics, the problem of making a perpetual motion machine. And the ultimate analysis of that problem was to see what work was. If you wanted to have work, you want to know what we found out that work was force times distance. And once we understood that, we came to realize that every time we devised a device, the force times the distance that went in equaled the force times the distance that came out. In fact, it was always so true that we began to take that as the rule. We assumed that would be true, which meant we assumed that you could not make a perpetual motion machine. And on the basis of that assumption, we were able to analyze various things. It's kind of interesting how physics began with people trying to make a perpetual motion machine, and then after failing for a long time, they took it as a principle that you could not make a perpetual motion machine, and then using that as a basic principle, they could analyze other machines, assuming that to be true. That was the key to the analysis of most of the machines that we thought about. So we thought a little bit about physics. Now, in this talk, I want to go back to the problem that got astronomy started. And of course, what got astronomy started was astrology. And what people wanted from astrology was to know the future. And the people believed long ago, and by long ago, I suppose I mean 500 BC or 1000 BC, 2000 BC, but also all through the Middle Ages and right up into Renaissance times, people believed that events on Earth were controlled by events in the heavens, that we on the Earth were ruled by the heavens, and that if we could only tell what was going to happen in the heavens, we could tell what was going to happen on the Earth. It was almost as if the feeling was that we on the Earth were puppets. And by we on the Earth, I not only mean people, I mean animals and forests and trees. Everything that happens on the Earth was a puppet, and that the strings from our arms went up to heaven, and that up in heaven there were forces and powers that manipulated us, maybe not in overt ways that made us raise our arm every time we scratched our head, but in very basic and powerful ways that we were controlled by forces that emanated from the things, the sun, the moon, and the stars, that emanated from the things up in the sky, and they controlled us. And people firmly believed this for thousands of years, and that motivated their actions. And that motivated them to try very hard to understand the future positions of the sun, moon, and stars in the sky. By future positions, I mean if we know where they are tonight, where in the sky will they be in a week from tonight, in a month from tonight, in a year from tonight? Now, to begin with, I want to ask, why did these people believe so strongly that they were controlled by things in the sky? Why did they believe in astrology? And the answer that, of course, you might hear nowadays is they were stupid, superstitious people. Well, that might be, but they were certainly no more stupid than modern people, and probably no more superstitious than modern people. They had less experience, there's no doubt about that. They hadn't flown in airplanes, but there are still plenty of people that fly in airplanes today that believe in superstitious, strange things. Of course, there are people today that still believe in astrology, but why did they believe in astrology? When I say most people today don't believe in astrology, of course, some people will claim to believe in astrology today, and some people genuinely do. But you can kind of put them to a test. You know, it's true that on a first date, you might ask your boyfriend or girlfriend, what sign are you? Are you a Sagittarius or a Virgo? And does a Virgo go well with a Sagittarius or something like that? But when it comes to the serious decisions of life, when it comes to the decision of what school you should go to, or later on a decision of if you should buy a house or if you should rent, or even a greater decision if you should have an operation, for those things, in all likelihood, you will not go to an astrologer, and you would not think of going to an astrologer. But there was a time long ago when people would seriously consider consulting an astrologer for very important decisions like that. So I want to go back to that day and try to go inside of those people's heads and tell you why they believed that events on earth were controlled by things that happened in heaven, specifically the motion of the sun, moon, and stars. Okay, let's begin. Everybody that's looking at this tape did something this morning, and they did it at approximately the same time. The various people who are looking at the tape don't even know each other. They're all strangers. Even now, they don't know each other. Nevertheless, this morning, or whatever morning anyone happens to be looking at this tape, you did something together, and that thing that you did together was you all got out of bed at approximately the same time, sometime shortly after 6 o'clock. And there's indeed something that you will all do again together, and that is you'll all probably go to bed together. And in that, you are ruled and controlled by the sun. It's curious how strongly you're ruled by the sun because, you know, nowadays you have electric lights. You really don't have to get up with the sun, and you really don't have to go to bed in such a way that you can get up when the sun comes up. But nevertheless, everybody does it together. You can imagine how much more people were controlled by the sun long ago when there were no electric lights. Indeed, when there were, there was no gas. And a candle long ago was a very valuable thing. Most people did not have candles. I think candles were very rare. In fact, in the olden days, life must have been very much like it is when you go camping. You know how it is when you go camping and you're up in the Sierras or up in the mountains? About the time it's beginning to get dark, you have your firewood gathered and you have your hot dogs laid out. And as soon as the sun's on the horizon, that fire is going and you're cooking your hot dogs. And then after you eat your hot dogs and the sun's down, that's it. The fire goes out and you go to bed. And in the morning, when the sun comes up, nobody sleeps late. When you're camping, as soon as the sun gets on the horizon, you get out of your bed, don't you? You get out of that sack and you begin to move around. You're absolutely controlled by the sun. So in that regard, it's not a superstition. It's exactly true. The basic thesis of astrology, that people on the earth are controlled by the sun, is precisely and exactly true. Now, you're not only controlled by the sun on a daily basis, on a 24-hour basis, but you're also controlled by the sun on a yearly basis. What is the yearly cycle of the sun? The yearly cycle of the sun, let's start in summer. In summer, the sun is high. Of course, it's high if you live in the United States or Canada or Europe or in Japan or in Asia. The sun is high overhead in summer. And the days are long, and it's rather hot. But then the summer wanes, and lo and behold, eventually you go into winter. And what happens in winter? In winter, the sun is not high in the sky. Even at noontime, the sun is still low in the sky, and shadows are long. And the day is not long. In winter, the day is short, and the night is long, and it's cold. And of course, there's all the consequences of the fact that cold in winter causes snow and ice, while heat in the summer causes it to be hot and balmy. And as the sun changes from its summer position to its winter position, it changes life for people on the earth. Life is entirely changed for a person on the earth. In the summer, the living is easy. You know, there's a lot of fruit Here in California, everybody is trying to give away free zucchini. And there are grapes and apples. People let the apples fall on the ground, and the cherries too, and the peaches. It always kind of amazes me to see people who receive food stamps right in their front yard, having a tree full of fruit, and the fruit falls on the ground and rots in the summertime. The living is easy. You don't even have to live inside. And in summertime, you can sleep on the roof or sleep on your porch or go out on a trip and sleep by the creek. Life is easy and pleasant. But in winter, it's a different sort of situation. In winter, you can be hungry. You can look at the tree and there will be no fruit on the tree. There won't even be any leaves on the tree. It's cold. You can't sleep outside. And the ground is muddy and wet, and you can't even do any work outside. If you have to work in the winter, it's miserable conditions. You can't even move a heavy object because you'd have to move it through the mud, and you can't get yourself through the mud or your horse through the mud or your tractor through your mud. And what's more, in winter, the worst thing of all is that people have to go to school and you're held as a prisoner against your will. So winter is very different than summer. And what controls this? The sun. The sun controls this. Not only does the sun control how people live different lives from summer to winter, but the sun even controls the animals. Some of the animals even spend the summer going to the winter. They spend the winter going to sleep. It's so miserable that they get in a cave and go to sleep for the winter. But of course, during the summer, most of the animals have a pretty good time. And not only does the sun control the animals, it even controls the trees. The trees have leaves and fruit in summer, and during the winter, they're bare. And not only does the sun control the trees, the sun even seems to control almost inanimate objects like the rivers. In winter, the rivers are full of ice, and come springtime, the rivers are full of water, and then during summer, maybe they dry out again. The sun has enormous control on absolutely everything you can think of on the earth. So it's not mythology that the sun rules the earth. You can just open your eyes and look around, and you will see that it's an absolute empirical fact that the earth is ruled in a million different ways by the sun. And of course, the ancient people had eyes, and they were wise people, and they looked around, and they were fully aware of this, certainly as aware as we are. Okay, so much for the sun. Now let's go to the moon. What effect does the moon have on people on the earth? Well, it turns out that it's very likely that the first people on the earth made their living from the sea. And the reason that they possibly made their living from the sea is that if you chase a live animal that's running away from you, it's kind of hard to catch it. But if you go to the sea and you catch a crab or a clam or an oyster, it can't run very fast, and you can pick it up. And so the living is easy on the seashore. There are a lot of good things to eat that are easy to catch on the seashore. So it's very likely that people were first attracted to the sea to make their living. And even if you try a little harder, it's certainly easier to net a fish than it is to chase down an animal that you have to run after with a spear. Even to this day, if we look at a map of the world, you will see that with just a few exceptions, practically all of the big cities of the world are on the ocean. Someplace on the ocean with a seaport are the big cities of the world. So people are still drawn to the sea. Now, anyone who spends much time by the ocean is going to know that something happens periodically at the ocean. Periodically at the ocean comes in, the water gets high. And when it gets high, it covers the beach. Water comes flowing in. And in fact, sometimes it covers the whole beach, though there is no beach at all. The water's right up against the cliffs and the rocks. So the water comes way, if it's flat land like in Louisiana, the water comes way, way, way inland. It floods inland. But then just a few hours later, the water becomes low and it runs off and the beach is exposed, and sometimes you can see way out to the ocean and you can see rocks out there. And that's very important, because if you want to go out there and catch some oysters, or crabs, that's the time to do it, when you can go way, way out in the sea on dry beach. And people were aware that there are times when the water comes in and when it goes out. Of course, you know that those things are referred to as high tide and low tide. Now, I recall experience with a young friend of mine, or I should say an inexperienced friend of mine. And one morning we went over a bridge, and you could see in the bay that the bay was high. It was high tide. And we came back several weeks later in the morning over the same bridge, and the tide was low. And she was most amazed, the fact that here we are at the same time of day, and first the tide was high, and now a few weeks later, the tide is low. How can it be that in the morning you should either have high tide or low tide? You can't have one or the other. But it turns out that the time when there is a high tide is not tied to the sun. If it were tied to the sun, then there'd always be a high tide in the morning or a high tide in the evening or at some particular time that's related to the sun. But the tide is not tied to the sun. The tide is tied to the moon, and the ancient people knew that. What do I mean by saying that the tide is tied to the moon? I mean this. I mean at the time when the moon is, say, rising, there is a high tide. Or maybe it's a time when the moon is overhead. There is a high tide. It doesn't matter which. But the next day, when the moon is rising or when the moon is overhead, whichever position the moon was in the previous day, the tide will come back to its same height when the moon comes back to its same position in the sky. Now, it turns out that the moon does not always rise at the same time. I'm sure you know that. You've seen moonrise. Sometimes the moon rises at sunset. Just when the sun goes down, the moon comes up. Sometimes the moon rises at midnight. Sometimes the moon doesn't rise at all. You've seen the moon in all different positions in the sky, and you can tell that it has to be in all different positions because the moon moves once around the sky every month. What's that? 28 days. So the moon occupies all possible positions around the sky in a 28-day period. So it's going to rise sometimes at sunrise, sometimes at sunset, sometimes at noon. The moon will have all different positions. But the point of the story is that whenever the moon comes back to the same position in the sky, which might be at a different time of the day, depending upon when the moon rises, different time of the solar day, when the moon comes back to the same position in the sky, the tide comes back to the same position. It's high tide or low tide or whatever it was on the previous day. Now, the tide, that's not the moon's only influence on the tide. The moon has a double hold on the tide. What do I mean by a double hold? Well, it turns out that all high tides are not equally high, and all low tides are not equally low. There is a cycle in the month when you have when the high tides are not very high, and then the high tides get to be higher highs, higher highs, higher highs, and then they go back to lower highs, lower highs, lower highs. And it turns out that the low tides are not all equally low. Some low tides are, at certain times of the month, the low tides are much lower than other times. And it's a fact that whenever there's a high tide, that same day, there's also a very low tide. High tides and low tides go together. Very high tides and very low tides go together. And then if there's not very much of a high tide, there's also not very much of a low tide. But the important thing is that that is connected to the moon too. And it's connected to the phase of the moon. You see, when you have a full moon, then you have very high tides. And you also have very low tides. Both of them get exaggerated when you have a full moon. But when you have a moon that is what's called a first quarter or a last quarter moon, that's a moon that looks like this, which a lot of people call a half moon, but the right word is a quarter moon. When you have a quarter moon in the sky, then the tides are not very high. The highs are not high and the lows are not very low. But finally, when the moon gets over to the phase like this, when it's just a crescent in the sky, just a sliver, That's very close to the new moon when it's just a sliver in the sky. Then the tides are very high. The highs are very high and the lows are very low. So there's these three basic phases. When you have a full moon, then you have very high highs and low lows. Not much tide on the first quarter or the last quarter, but when you get to the crescent moon, that's the new moon, then you have, again, tides, just almost like for a full moon. So the moon has that control on the ocean. And the ancient people were fully aware of that. They did not know the reason why. That's a fact. And if they had some ideas as to what the reason, it was probably wrong. But they knew that there was a connection, that the moon controlled the ocean. Not only does the moon control the ocean in their mind, but there are other connections between the moon. Let's take this. People have a menstrual cycle. How many days in the menstrual cycle? 28 days. And the moon goes around the earth. How long, if the moon is full, before there's another full moon? After the full moon, the moon wanes, and finally it turns into a crescent, disappears, and then a new crescent appears, and it gets fatter and fatter, and eventually you get to another new moon. How many days between two new moons? 28 days. Now, I'm not saying that there is a connection between those two things, and I can give a strong argument that there is no connection between them. I suspect it's just a coincidence that the two things come out the same number. But the ancient people could count to 28, and they certainly realized that it seems strange that they should both be on the same number. And all that really is important is not what is, but what is in people's heads. And so in people's heads, they thought that there must be a connection. Not only does the moon control things by the sea and water, but even if you go inland, the moon controls things. And I will tell you just a little story. When I was a kid, I spent a lot of time at a school, a boarding school. And there were various kids at that school that did various things. It was called Van Horn School. And in those days, it was far out in the country. Now it's probably a fancy subdivision. But in those days, it was far out in the country and quite dark. And the kids were supposed to do their homework and their studying, and they did, particularly on a night when there was no moon in the sky. If you were in the crescent moon or in the dark of the moon, nobody would go out and horse around. They'd stay in, and indeed they would learn their spelling or their arithmetic or writing their composition, whatever the poor devil had to do that night. But on the night of the full moon, when you could see outside, you always knew it was just a matter of time before some kid was going to go in his room and close the door and crawl out the window. And then some other kids would be crawling out the window, and they'd throw rocks at each other, or throw rocks at the chicken coop, or throw rocks at the girls' dormitory. Or there'd always be some shenanigans going on the night of the full moon, because on the full moon you can see. You see, if you try to go outside when there is no moon, and you go into an orchard, like was outside of the window of the dorm where I lived, and you ran around out there in the dark of the moon, and it was really dark in those days. There were no lights. You wouldn't go too far before you'd end up walking into a tree. And if not into a tree, you'd at least run your face into a branch, and that was pretty nasty. But on the night of the full moon outside, it was like a playground. You could see everything. And of course, it's not only the kids and the people that go out and act differently on the night when there's a moon, but the animals too. The animals can run around. The animals have freedom to operate. While in the dark, when the moon is dark, then a lot of the animals can't see. I suppose there are some that can see in the dark, and they have a great advantage. But for the most of us, they're paralyzed in the dark of the moon. So the dark of the moon must surely affect hunters and animals that are hunted in the dark. Well, so much for the moon. So I've showed you how the sun and the moon affect the earth, at least as seen by the ancient people, how it affected the earth. I want to go on now and talk about the planets. You remember that we look up in the sky, the night sky, it's full of stars, but there are a few very bright stars in the sky that don't stay in the same position. Oh, if you go up and look the next night, and the next night, if you just look for 3 or 4 nights in a row, they'll be very much in the same position. It will seem that they're standing still. But if you carefully watch them over a period of a month, you will see that these stars don't stay in one place. They wander around. They first are in one constellation, and then after a while they wander to another constellation, and then they wander to another constellation. The stars, as far as the ancient people could tell, were prisoners and forever remained frozen in a particular constellation, but not the planets. They could wander around. So let's talk a little bit about the planets and see what effect the planets have on life on Earth, or particular on people on Earth. And to begin with, what planet shall we talk about first? Well, years ago, if I gave a talk like this and I asked that question, I said, what planet should we talk about first? I didn't have to worry, because inevitably the audience would answer, the first planet we want to talk about is Mars. Not so much anymore. Now people might want to talk about Jupiter or Saturn or something like that. But back a few decades ago, everybody wanted to talk about Mars. And of course, the reason is that Mars received a lot of publicity in the newspaper and indeed on the radio, because back at the turn of the century in the 1920s, there was thought that there were canals on Mars and there were people on Mars, and there was so much publicity generated about that the name Mars was really a special name. I guess that's why they named candy bars after it. So let's begin by talking about the planet Mars. Well, I'll tell you a little bit about Mars. If you just look at Mars with the naked eye, it's not very impressive. It's a rather faint star, or maybe I should call it planet. I'll call it star, because most people actually do call it a star. It's faint. It's so faint that if you look at it from a big city, you might have a difficult time seeing it. It's about as faint as one of the stars in the Big Dipper. Most people who live in the city don't see the Big Dipper. On a camping trip or out in the country for the first time, say, oh, look, there's the Big Dipper. But in the city, you can't see things. Those are second magnitude stars, and you can't see them from the city. You can't see Mars very easily from a city because it's rather faint. But something happens approximately every 2 years, not exactly every 2 years, but approximately every 2 years. Mars gets very bright. So bright that I can see its color. Now that's something special, because I'm legally colorblind. On a television monitor, when you turn down the color volume and you get it towards black and white, other people in the room can see color, but quickly the color fades for me. For a legally colorblind person to see color, the source of the light must be very bright. It turns out that Mars gets so bright in the sky, approximately once every 2 years, that even I can clearly see that it has color. And of course, you know what color it has. It has the color red. And incidentally, when it gets bright, it's up in the center of the sky at midnight. In other words, it turns out on these, Mars isn't always overhead at midnight. In fact, most of the time Mars is to the west of the sky or to the east of the sky. Sometimes Mars isn't even in the sky at all. But on those occasions when Mars gets big and bright, it is almost directly overhead at midnight. And that happens every 2 years on the average. And then for the rest of the time, you can't see Mars at all. Or you can see it. Nowadays in the city, you have a hard time, but it's an innocuous, inconspicuous object. Now, what's the reason for that? Well, the answer as to what is the reason for that, the ancient people did not know what the reason for that was. They didn't know why. I'm going to leap ahead with you and show you the reason. But then, you know something that the ancient people didn't know. Here's the reason. Here's the orbit of Mars, and I'll put an M here to show you that this is the orbit of Mars. And in the center of the solar system is the sun, and here is the Earth. And I'll put an E here for the Earth. Now, it turns out that the Earth and Mars don't stay in one position, but the Earth gradually moves around its orbit. Isn't that right? Once around in 1 year, and once around in 2 years. And of course, Mars moves around too, but not as fast. And after a while, what will happen is Mars won't be here anymore. It'll be gone, and it'll move over to some other position in its orbit over here. And the Earth won't stay there either. The Earth might have been here to begin with, but after a while, it will move over to some other position in its orbit, stay here. So like when we started, they were close together. After a while, they will be far apart. But they won't always stay far apart. After a while, they'll turn so that they will get together again someplace else. Now, it might not be here. Maybe after this goes around for a while, it'll happen that by the time Mars gets over here, the Earth will go around a couple of times, and the Earth will get over here, and then they'll be close together again. And that happens approximately every 2 years. Now I have to be like the judge and the jury, and I have to instruct you to forget about what I've just told you. You are instructed to disregard this, because to know this would put you way ahead of our story. And I'm trying to tell you about how the world was seen by the people who lived way back in 500 BC. And of course, they didn't have this picture of the world at all. All they knew is that Mars got big and bright once every 2 years on average. Now, I have to tell you about something else. I'd like to tell you about what most people did in the olden days. Most people who lived in the civilized world, what was their occupation? Almost everybody in the olden days was a farmer. There were very few people in those days who lived in cities. Cities were very special places to live. And to live in a city, it was hard to make a living. And you had to have a very special craft, or a very special trade, or a very special business. You found people who knew something very or had a trade, or were in the business of buying things and selling things, were professional traders. They lived in cities, but they were very few people. 99 out of 100 people were farmers and lived out in the country. And indeed, I dare say, if you look back in your own family, perhaps not to your parents, but probably to your grandparents. And if I look back to my grandparents, and certainly to my great-grandparents, they were people who made their living in the country. And that is true for almost everybody today. Going back to your great-grandparents, you will find people who lived in the country. And of course, people who lived in the country made their business from agriculture, which means from farming. Now, the life of a farmer has a cycle to it. And the busiest time, let's say life for the farmer begins in the spring. In the spring, the farmer is very busy because as soon as the fields are dry, that is, as soon as the mud is gone, the farmer is out there planting seeds. And no sooner do the seeds get planted than the farmer spends the whole summer fighting weeds and fighting locusts and protecting his plants, probably even protecting them from the sheriff. But at any rate, the man is protecting what he's trying to grow, no matter what it is. And then comes the fall. And in the fall, you have to bring in your crop. But you have to bring it in before the first rains, because if the rains hit the grapes or the rains hit the grain, the rain will damage and destroy the stuff. And so throughout the spring and the summer and the fall, the farmer is working his tail off. Finally comes winter. And in winter, of course, it's cold outside. The ground is maybe covered with snow, maybe with ice. If it's not snow and ice, it's at least covered with mud. and you can't work in those circumstances. So there's one time of the year when the farmer can't do anything, and that is winter. And that's traditionally the time that people go to school. Why do people go to school in winter? Because there's nothing more useful to do, so you might as well read a book while it's raining and muddy outside. So much for that. Now there's one other thing that happens during the summer. One other possible activity that people like to deal in that occurs during the summer, and that is this. There is a time for war. What is the time for war? The time for war is summertime. Why is summertime the time for war? Because you can't fight in winter. A lot of people tried and a lot of people died. Napoleon tried to fight in Russia in the winter, and everybody knows what happened to him. And Hitler tried the same thing, to fight in the winter in the same place, and everybody knows what happened to him. There is a famous picture which used to grace every American schoolhouse. I don't know, maybe it's unconstitutional to have the picture up anymore, but it was a picture of George Washington crossing a river. What was it? The Delaware River? I think it's the Delaware River, and in wintertime to attack the British in their camp at Trent. During the winter, during the Revolutionary War, the British made their camp their winter camp at Trent, and George Washington surprised them by attacking them in winter. Of course, the British expected no one in his right mind to attack in wintertime. And the real victory in that attack was not the British. The British were so surprised that it was an easy victory. Indeed, the painting doesn't depict Washington's victory over the British. It doesn't show the British general surrendering his sword to George Washington. That's not what the picture shows. The picture shows and celebrates Washington's victory over the Delaware River, which was a very difficult thing to cross in the ice. Apparently, the big floating pieces of ice are big, nasty, mean things that will squash your boat, and it was a most difficult and daring thing. The real trick was to be able to cross the river in winter. But as a rule, most people don't fight in winter. A good war begins in the spring, is pursued in the summer, and is concluded in the fall, because that is the time when you can move soldiers. Now you see you have a little conflict right away, because men should be busy working on their farms. The busiest time of the year is the summertime. But also, if you want to fight a war, summertime is the time to fight the war. But you can't do both. You can't be fighting a war and running your farm at the same time. So from ancient times, a cycle began. People would spend 1 year working the farm. And then if they had a good crop and they brought in a lot, they were okay. And they could go off on a campaign the next summer. See, the summer after the good harvest, they could go off to camp and have a good time and have a little war. But then the next summer after that, in other words, the third year, they couldn't be out fighting again, because now somebody had to take care of the farm and bring in some crops. So they'd fight for one summer, and then they would come home and take care of the crops for the next summer. And maybe if things went well on the farm, then the summer after that summer, they could go out and fight again. People always say that hungry people fight, and that, if people are hungry, they're going to fight. Well, I've heard that so many times, but it's entirely impossible and not true. Hungry people don't fight and can't fight. Well-fed people have to fight, and so they have to have a good summer to have a good fight. At any rate, you see what I'm driving at right here. Wars have an ancient cycle. From ancient times, they have this. A war is fought on a 2-year cycle. One summer they have war, and the next summer peace, and the next summer war, and the next summer peace. And indeed, that cycle continued even through the Revolutionary War in the United States. A lot of George Washington's soldiers, when summertime came, would decide that they had to go home. Since they had been with George Washington the previous summer, the following summer, they just expected that it was understood that they would go home. It was not mutiny, it was just understood. Of course, George Washington did not particularly like that, but the soldiers said, what the heck, we have to go home. We were here last summer. This summer we have to take care of business at home. Well, now I think you can put together things and you can see exactly where I'm leading. Mars is on a 2-year cycle. Approximately every 2 years, Mars appears in the sky, big and red. And approximately every 2 years is the cycle of war. The two things have quite a connection, and it's not hard to see how Mars became the god of war. Okay, enough for Mars. Let's leave Mars alone and go out in the solar system, and we go out to the next. What's the next thing further out from the sun beyond Mars? It turns out that if you go out from Mars, the next thing further out is something called the asteroid belt. There's a thing there that's made of many pieces of rock or pieces of a planet, I don't know. Probably the biggest ones are a few hundred miles in diameter. Most of them aren't even round. Most of them are probably as big as your thumbnail and even smaller. And these are the asteroids. A lot of stories told about the asteroids, but I can skip them. I don't have to talk about them because the ancient people did not even know they were there. It's a very interesting story about how they first came to be discovered. But that's not for this talk. The asteroids were unknown to the ancient people. So we pass through the asteroid belt as if it wasn't there. And we go out further and further, and finally we come to the next planet. What's the name of the next planet out from Jupiter beyond? I gave the answer, didn't I? Out from Mars through the asteroid belt. The next planet out is Jupiter. So I'm going to talk about Jupiter. What god is Jupiter associated with? Jupiter is associated with the god of gods, the chief god, the Machismo god. Isn't that right? Jupiter is the heavyweight of gods, the boss god, the man god. How did Jupiter get to be the heavyweight god, the man god, the god of gods? How did that come to be? I'll tell you how it came to be, or you might think. Well, let me ask you how it came to be. You might think, well, gee, Jupiter's the biggest planet, isn't it? Jupiter's the heaviest planet. Well, since Jupiter is the biggest, heaviest planet, it should be the biggest, heaviest god. It should be the man god, the Machismo god, and that's why. But is that the right answer? No, that's not the right answer. That couldn't be the right answer. Because these ancient people who were looking at these things had no idea of what their size was. And they had no idea of what their weight was. Indeed, if you asked them what their weight was, they would tell you that the things they were looking at in the sky, the planets, had no weight at all. They were weightless lights. Because if they did have weights, they would fall onto the surface of the earth, like a brick. You see, the attitude that these people had as to what these things, these planets and stars were in the sky, was very much the attitude that you have when you go into a planetarium and you're sitting there in the seat and they show you a planet in the sky above you, or the moon in the sky above you, or the star in a planetarium. When you're seated in a planetarium and you see those things on the dome of the sky, you know that they're not real things. They're apparitions. They are lights that are projected there by the machine in the center of the room. Indeed, the machine in the center of the room has all kinds of special lenses in it to produce those effects up there. But you know the thing is not real. It is not, well, of course it's real, but it's not a material object. It's just a light striking a wall. It's just like when you go into a movie theater, you know the actors are not really on the screen. They're just lights on the screen that are bright and dark, where the actor's face is bright and dark, dark on his mustache and white on his teeth. And that's what you're looking at. And that is the attitude that the ancient people had about these things in the sky, that they were just lights up there. They were not material things. So the ideas to size and weight never entered their mind. So that is not why the ancient people thought of Jupiter as the man god. So what is the reason? Where did they get the idea from that Jupiter was a man god? Well, now I'll tell you something else. If Jupiter is in a certain place in the sky tonight, in a certain constellation, then in 1 year from now, it will probably not be in that constellation anymore, but it will move to the next constellation. And it will move to the next constellation and the next constellation. And after a while, it will move all the way around the sky, through all the constellations. There are about 12 constellations in the path of the sky that Jupiter moves through. And after a while, it will be a long while, but after a while, Jupiter will finally return to just about, not exactly, but just about the same part of the sky that it was in before. And how many years does it take to do that? Well, it takes about 1 year to pass through each of these constellations. So in approximately 12 or 13 years, the exact number eludes me, but it's about 12 or 13 years, Jupiter will come back to whatever position it is in tonight. It will be back there in about 12 or 13 years in the future. Now, there's something there's something that happens in about 12 or 13 years. If a boy is born, at first he's a little kid, and he grows up, and he grows up, and pretty soon he gets to be 4 years old, and 5 years old, and 10 years old, and pretty soon he gets to be 13 years old. What happens when a kid gets to be 13 years old? In just about every civilization on Earth, particularly every old civilization on Earth, when a boy becomes 13 years old, he is deemed to have become a man. He is confirmed in his church, or he is bar mitzvah, or he holds up a liquor store, or he does whatever he's supposed to do to demonstrate the fact that he's a man. And so that is the story of Jupiter. When the planet Jupiter returns to the position it was in the sky, when a boy baby is born, that is the time, traditionally, that the boy baby becomes a man. You might think that 13 or 12 is rather young to become a man, but it's probably not, because in those days, how long did people live? The average age of life in those days was about 30 years. And it's not hard to see why it was about 30 years, because by the time you're 30 years old, you've probably come down with an infection that was serious enough that the doctor gave you penicillin, or one of the modern equivalents of penicillin. Either it was an infection in your teeth, or God knows, a cut, or something like that. But I don't think that many people reach the age of 30 before they have been treated with penicillin. Not only penicillin for a trivial thing, not penicillin as a safeguard, but penicillin as a very essential thing in the cure of the infection that the person had. Now, not in those days, not long ago, people didn't have penicillin. They didn't have sulfa drugs. They didn't have even the sense maybe to be clean like we are, if we are clean. And they died very easily, because if the doctor doesn't have that medicine and you get the infection, you're up the creek real bad. So it's not surprising to see that people would die at the age of 30. So when you're 13, you're more than a third of the way through your life, way more than a third of the way through your life. So if ever you're going to be a man, you better be a man then, or else your whole life would be gone. Okay, so much for Jupiter. And we see that apparently Jupiter really does have some connection. The cycle of Jupiter has a connection with life on the Earth. Well, let's do just one more. Let's go out just one more planet. And if we go out just one more planet from Jupiter, what's the next planet further out? The next planet out from Jupiter is Saturn. Saturn was on the edge of the ancient solar system. Of course, now people with telescopes have seen that there are planets in space further out than Saturn. But in ancient times, if you were at Saturn, That's as far out as the solar system went. That was the last stop. That was the end of the world. Of course, what is Saturn? Saturn is that beautiful ringed planet. But again, you know it has rings, but the ancient people did not know it had rings. That took a telescope to discover. Indeed, the very first telescopes did not even show that Saturn had rings. The very first telescopes that people made gave people the idea that Saturn had 2 ears rather than 2 rings. So it took a halfway decent telescope to show that Saturn had rings. Well, in the mind, let's look at Saturn as the ancient people saw it. And let me ask you what god Saturn is associated with. I'll bet most people can't answer that. You know, Jupiter is Machismo, Mars is war, Venus is beauty, Neptune is the sea, Pluto is the underworld, Venus is, Mercury is speed and the messenger, isn't that right? Everybody knows those things. But if I ask you what god does Saturn represent, I'll bet there's a lot of you who don't know. I chide those people who imagine that they are interested in astrology and don't know that. But I didn't know it myself until I saw a statue one day of Saturn, and I was a little surprised when I saw the statue of Saturn, the god Saturn. The god Saturn is depicted as the Grim Reaper. I'm sure you've seen these things on New Year's. A lot of the art of New Year's shows a new baby. There's a picture of a new baby on one hand, and on the other hand there's the old man, and the old man is bent over, and he might have a hat on, or he might be bald-headed, and he has a sigh because he's cutting grain down. Of course, what it means is it's the end of life, and he's cutting life. He's making an end of things with his sigh. That old man with the reaper. That god, the old man with the reaper, is the god that is depicted by Saturn. How did that come to be? How did it come to be that Saturn is picked as the god of old age? And you can kind of see it too. The name Saturn means Saturnalia, or senility. And so how did Saturn get to be the god of old age? Well, you can kind of see that. It's not hard if you know just one thing. And you can guess what you should ask. You should ask me, how long does it take Saturn to go around the sky? If you see Saturn in a certain constellation in the sky tonight, it will gradually move out of that constellation. It moves much slower than Jupiter, of course, because it's further out. But eventually, after quite a while, Saturn will come back to that same constellation that it started from again. How many years do you think it will take for Saturn to go all the way around the sky through all 12 constellations of the zodiac and come back to its first constellation? The answer is it will take approximately 30 years, and that's the key. In the olden days, people lived about 30 years. So when Saturn came back to the constellation, which it was in when you were born, when it got there, it was time that you had your affairs in order. You better write your will, figure out who your heirs were, and be ready to close down your ship, because that was the time of a completed life, 30 years. Incidentally, Saturn, another idea that Saturn was associated with in the olden days was wealth. The Roman treasury was in the temple of Saturn. They kept I suppose that the bureaucrats in those days were like the bureaucrats today, and they took the temples and turned them into offices, and the treasurer decided that he would take the temple of Saturn to be his office. But of course there's some symbolic reasoning to that. Wealth is associated with old people. Of course, when a baby is born, the baby doesn't have a dime to its name. In fact, the baby doesn't even have a pair of pants to its name. It's born naked. But if people squirrel away a little bit of money every day in their life, every year in their life, when will they have the most money squirreled away? When they're oldest, isn't that right? When they come time to deal with Saturn. So that's That's the connection there. Well, enough of this and that. Now, I have shown you that the various planets and the sun and the moon in the sky, remember the thesis of astrology was that these things somehow do have some influence, some basic and fundamental influence on life on Earth. And I think I've showed that there is that basic connection. So it's like this. What scientists are always looking for is a consistency principle. Let me explain. Supposing I have a machine here, and there's a button, and I push it, and out here comes a nice sandwich. And then I push a button here, and out comes a nice Coca-Cola. And then I push another button here, and out comes a nice piece of candy of some sort. And then maybe I push another button here, and out comes a bowl of chicken soup. And then I push a button here, and out comes a fist and hits me in the face. I'm very upset because I expected consistency. Nice things were coming out from everything in this machine. I had every reason in the world to expect nature to be consistent, and I had a reason to expect that something good to eat should have come out of here, maybe an apple. But no, a fist came out, and I'm very upset. Now, it could have been bad. Had I pushed this button and a draft notice came out, had I hit this button and a subpoena came out, had I hit this button and a traffic ticket came out, had I hit this button and had a notice that my electricity was going to be turned off come out, and then had I hit this one and a fist came out and hit me in the face, I would not be surprised at all because there would be consistency. But the one thing that scientists seek, and that every rational person seeks, is consistency. And so, if you discover that there is a connection between things that the sun does and what happens to people, and what the moon does and what happens to people, and what Mars and Jupiter and Saturn do and what happens to people on the Earth, then there's every reason to believe that if something new in the sky appears, like a comet, which wasn't there before, a good scientist should say, well, all these other things affect people on the Earth, therefore the comet must somehow affect people on the Earth. Let me look at the people on the Earth and see if there's any effect that that comet has. And on the other hand, if very big things happen on the Earth, like the tides or like the seasons, suppose one day there comes to be a plague on the Earth that there was not here before, like cholera. It was not here last year, it was not here the year before, but suddenly this enormous plague comes that affects, it seems to affect the whole Earth. We say, where could it have come from? It must be, the things that affect the whole world must be things that come from the sky. And there's every reason to look up in the sky and see if there is some strange configuration of the stars or some new star or something different in the sky that has caused this. And the people who would think this way would not be fools. The people who would think this way would just be good scientists looking for consistency, looking for some unifying principle. In fact, the same people who would be delighted by finding that all the levers have the same explanation ultimately, the same kind of person with the same mentality would be seeking to explore astrology to find out what other effects there might be from the sky on the Earth. And so that is how astrology got started and how it became such a strong influence in the heads of thinking people, not only in Europe, but all over the world where there were civilizations, in China, in Central America, all of these different people who probably had very little contact with each other independently became fascinated by what might be found from studying the planets and the effects that they had. They weren't interested in the planets in and of themselves. They were just lights. They were interested in what effects these things might have on people on the Earth. Okay, so much for that. Well, I'll leave you with a little puzzle. You can see how how astrology in and of itself was a very powerful and interesting historical subject. Now, if you talk to modern day astronomers, one of the things that they will continuously put down, they'll treat it almost like a devil, is astrology. They will go out of their way to bash astrology. Now, astrology seems to be, of all the strange and bad things that are going on in the world today, astrology, while it might not be very useful in the modern world, does not seem to be a great hazard either. And you might wonder, why are astronomers making such a great effort to put down and criticize astrologers? It's almost like a religious crusade they have. Well, you might think about that, and I'll leave that as the puzzle for our next talk. Bye-bye.